Question 3, part A, starts off with a very simple question. State what is meant by the term hydrocarbon. Most students have got this absolutely right. A compound or a molecule containing hydrogen and carbon only. The few students who have got it wrong was for this very reason, that they failed to mention the word only. This is absolutely vital. Part 2 of the same question. A molecule of decane contains 10 carbon atoms. State the molecular formula of decane. Decane is for 10. Again, very simple. Using CnH2n plus 2. N here, it will be 10. 2n is 20 plus 2 is 22, which will give you the molecular formula of decane, C10H22. Part 3 again, not too complicated at all. All you have to do here is work out the empirical formula of decane, and we've already been hopefully correctly given C10, which goes to C5. Simply cancelling down 10 to 5, or dividing 10 by 2 will give you 5, and equally dividing 22 by 2 should give you 11, to give you the empirical formula C5H11. Part B of this question is referring to dodecane. Dodecane is decane with 2 extra carbons, which will give you 12 carbons and 26 hydrogens, again according to CnH2n plus 2. We're told it's a straight chain alkane that reacts with chlorine, which is Cl2, to produce a compound with the molecular formula C12H25Cl. And straight away you should be able to notice from here that when you look at the original molecule C12H26, dodecane, and the newly formed compound C12H25Cl, we have one hydrogen short here, as well as having an extra chlorine, which means that one of these hydrogens here has been replaced by a chlorine. We are given the equation here, and we're told that utilizing Cl2, we release a HCl molecule. Again, the hydrogen comes from here, and one chlorine comes from here. We're told that the reaction is initiated by the formation of chlorine, free radicals from chlorine, and we're asked what is meant by the term free radical. Again, most people have got it right, and the correct definition or answer could be a particle or a chemical species that contains a single unpaired electron. Equally, you could have said a molecule, ion, or group of atoms that contain a single unpaired electron. Where a few people have gone wrong, they've actually stated, rather than particle, they've put down an atom that contains a single unpaired electron, which could be true, for example, chlorine, but then again, that does not take into account, for example, a methyl radical, because a methyl radical is not an atom. So the best thing to say is a particle or a chemical species, and that takes into account all the different types of radicals. The next question asks us for the conditions necessary to bring about the formation of chlorine free radicals from Cl2. The simplest answer here would be UV light, although extreme temperatures could also be used. And in the final part of this question, we're asked to state the type of bond fission involved in the formation of chlorine free radicals. Again, if I will quickly remind you that in homolytic fission, if we have a chlorine molecule, one electron goes in that direction, one electron in that direction, and what we have is the bond is equally splitting on both sides, which is homolytic. If both electrons went to one side, that would be hetero, but in this case we can clearly see it's one electron each, therefore homolytic bond fission. Before I resume to the next page, just quickly going back to this question over here, you could have an atom, for example chlorine, behaving as a radical, and equally you could have CH3, which is a group of atoms behaving as a radical. Both of these are covered by the word particle. In this question, we're asked for the 2 propagation steps involved in the substitution of a dodecane molecule. The first step of propagation will always utilize a radical, which in our particular case will be the chlorine radical which we made in the very first step. The easiest way to identify a propagation reaction is to note that you will always have a radical on the reactant side as well as forming a radical on the product side. And you'll have exactly the same situation here, reactant, radical, and a product radical. Coming back to the first step, you start off with your original dodecane molecule, react it with the chlorine radical formed in the initiation step. This radical here will abstract or take away one hydrogen, so you're left with C12H25, which is what you have here, and you have the chlorine here, which came from there, and the hydrogen taken away from there ends up bonding with the chlorine to form hydrogen chloride. And we have exactly the same molecule which we started off there, forming the reactant in the next step of the reaction, which will react with a fresh chlorine molecule, and exactly the same thing happens, but this time this radical will extract the chlorine from here to form a chlorododecane molecule, and the remaining chlorine from here is forming a radical over here. Part 5 of this question was the one where students had the most problems with. Not many people actually managed to figure out the answer was 6. I'll try to explain why. I've drawn the dodecane skeletal formula over here, and if we start putting, for example, a chlorine onto position 1, that could be one of the isomers. We could easily have in a separate molecule, we could have had this same line over here. Rather than going over here, we could have it here. So the chlorine could be on position 1, or it could be on 2 or 3, or it could be on 4. Equally, it could have been on 5, and it could have also been on 6. Now, it could not have been on position 7. It would be absolutely impossible for it to be on position 7, and the reason for that is that the position 7 over here would be the same as the position over here, which was the position number 5. So once you've hit 1, 2, 3, 4, 5, 6, you no longer can have any more isomers on this side, because they would be exactly the same as the one on the opposite side. For example, if I call this 1 chlorododecane, I cannot call it 12 chlorododecane, because the 12 would be the same as the 1. So you can only have 6 different isomers in this particular case. Part C was slightly tricky. However, there's enough information in the initial part of the question for everybody to successfully answer this. And we're told that dodecane can be cracked. Now remember, cracking means breaking a long chain hydrocarbon into a shorter alkane and an even shorter alkene. And we're also told that in this particular case, what we have is the ratio between the ethene and straight chain alkane is 2 to 1. In other words, for every 1 molecule of the alkane, we will have 2 molecules of the ethene. Now what I would do in this particular equation is write down the reactants, which we've got over here, and without worrying about what the alkane is, I'd straight away start down writing I've got 2 of the ethene molecules, which is what I have over here. So what I'm doing is I'm taking the information from the question and I'm putting down over here 2 alkenes. So I can just sort that out. Once I've managed to figure out I've got 2 ethene molecules here, I can then work out how many atoms I have remaining to work out what the formula of the alkane would be. So again, how many atoms of carbon do I have? For 2 molecules of ethene, I have 4 carbon atoms utilized. I take away 4 from the 12 to leave behind the 8. Similarly, 2 times 4 is 8. Take away 26 will give me 18 hydrogens over here. And then it's a simple case of naming the alkane which I formed over here, which shouldn't be too much of a problem. Any hydrocarbon with 8 carbons in will be called octane. In part D, we have a very straightforward question regarding isomerization. Isomerization, remember, is a process in which a hydrocarbon or a straight chain hydrocarbon is converted into a branch chain hydrocarbon. And we are given the product formula, which is 2,2,3-trimethyl butane. And if I was to quickly label the molecule, I would have the labels as 1, 2, 3, 4, and you can clearly see that I have 2 methyls on position 2, and I have another methyl, which is this over here, on position 3, and the main chain is this over here, which is 4 carbons long, and therefore it's called a butane. In the next question, we talk about reforming, and again, a reminder for reforming is a process in which a hydrocarbon chain is converted into a cyclic compound with the release of hydrogen gas. In this particular case, we're told the product is methyl cyclohexane. The cyclohexane is that part over there, and the methyl is this part over here. And to balance the equation, we need H2. This is now a fully balanced equation. This question talks about the different boiling points of alkanes, which are plotted by the number of carbon atoms in the carbon chain over here. First question refers to what's the boiling point of octane, and again, very simple to do. Take a line coming from the 8 carbons going upwards, and then draw a cross, which will give you a boiling point of approximately 400 Kelvin. The next question is talking about hexadecane, which is 6 plus 10, giving us 16 carbons, and again drawing up from here and across will give you approximately 545 Kelvin. In part B, we're required to talk about a technique which can be used a technique which should be used to separate a mixture of alkanes. Straightforward answer, fractional distillation. Again, a quick reminder, fractional distillation is a technique used to separate 2 or more liquids which mix with each other and have different boiling points. Part C1, telling us isomerization. Again, isomerization is a process in which straight chain hydrocarbons are formed into branch chain hydrocarbon, and we're told it's producing some structural isomers. 3 of them were given to us, we have to draw the other 2. In this first case over here, what we've done is we've taken the methyl from 2 and 4 position and put them both on position 2, as we can see here. So this isomer here is a similar one to here, because we have a dimethyl here and we have a dimethyl here, and the last isomer is quite similar to isomer B. All we've done is move the methyl from position 2 and put it into position 3. In terms of the boiling point for the next question, oh sorry, I've missed out part B. For isomer B, 2-methyl pentane is a name for this isomer over here. The main chain is 1, 2, 3, 4, 5, and the 2-methyl is sticking out over here. Now we can come to this question. Isomers A, B, C have different boiling points. In the boxes below, list the isomers A, B, C in order of their boiling points. C isomer will have the lowest boiling point because it's the most difficult to pack together. If I show you the main chain in this case, it's this over here, and we have branches in 2 very awkward positions, which will make 2 molecules of this packing together quite difficult. So that will have the lowest boiling point. B, which is this isomer over here, has only got one branch, so it will have a higher boiling point, and isomer A has no branches at all, and therefore it will have the highest boiling point. Part 4 requires us to explain the order of the boiling points in the previous question. Pretty straightforward. The more branching, the lower the boiling point, because less energy is needed to separate the molecules. So 1 mark is for talking about the relationship between branching and either lower boiling point or less energy. And then the 2nd mark, you must mention this word over here, van der Waals forces or intermolecular forces, and explain how this is related to the length of the chain and the branches. Asked here to draw the structural formula of cyclohexane. Hexane is 6 carbons, which we have over here in a cycle, will give us cyclohexane. In any question, if they ask for the structural formula, which they have done so here, and you give them more information than what is required, i.e. the skeletal or the displayed, that would equally qualify for a mark. Another question about reforming now. Again, reforming is converting a straight chain hydrocarbon into a cyclic hydrocarbon with the release of hydrogen and a full balanced equation. A reason for why companies reform alkanes such as hexane, a variety of reasons. You can have better fuels, and the reason why the better fuels is because the branch chain hydrocarbons are more volatile and therefore make better fuels. Lower boiling point is saying the same thing as more volatile. Increasing octane rating, something to do with more of the automobile industry. I would actually refer to or prefer one of these first 3 answers over here. A bit of maths in the next question now. We're asked to calculate the percentage by mass of oxygen in this compound over here. Give your answer to 3 significant figures. 1 mark is for calculating the correct relative molecular mass of the compound, which is adding 3 methyl groups plus a carbon plus an OH. So you have over here 3 methyls of 45 plus the 12 plus the 17 for the OH will give you 74. And then dividing the total RMM of the compound by the relative atomic mass of oxygen, as that's what's asked for in the question. From the periodic table, oxygen is 16, divided by the total mass, 74, will give you an answer of 21.6, which is correct to 3 significant figures. Final part of the question is ending with a balanced equation for the complete combustion. Complete combustion means there is no carbon monoxide forming, only carbon dioxide forming, as is stated over here. Best way to do this equation, always put in the reactants plus O2, and of course we're told in the question you're forming CO2 plus H2O. Never try to balance the equation by balancing the oxygens or the hydrogens first. The very first thing you always balance in any chemical equation is the non-oxygen and hydrogen components. In this case, we know we have 4 carbons, 3 here plus 1 here, so we always balance the 4 carbon dioxides here. Once you work that out, it's a case of counting how many hydrogens you need and then balancing off with the oxygens.